Dear students, today we have a class on random experiments, random variables, and probability theory. This is the first section in which we will discuss about the random experiment, sample space, and their functions. So the first one is an experiment. The definition of an experiment is considered here. So we can define an experiment is an activity which can be repeated in more or less same condition and will have same specific outcome or outcomes. So a experiment can be generally defined into two ways. One is called the deterministic experiment and the other is called random experiment. So what is a deterministic experiment? So an experiment which can be repeated any number of times by anybody at any time or any place, but the outcome results in the same way. So everybody get the same result, then it is called a deterministic experiment. For example, if you take a glass of water and put some sugar in it, a spoon of sugar, then that will dissolve it. Using a spoon, we can dissolve it in it. But anybody do this, get the same result. So such type of experiment is called deterministic experiment. Another way, we have a only one and one outcome for the experiment, and the results remains the same for the persons, any persons who do the experiment. So the second one is a random experiment. So a random experiment, one characteristic is that it has more than one outcome. Suppose we planted uh, 10 seeds, so we cannot say that how many seeds will be germinated until they germinate. So there may be no seed germinated or 10 seeds germinated or any number between 0 and 10. So there are more than one outcome and the results of the experiment should be predicted or get only after the completion of the experiment. Such experiments are called the random experiments. So an experiment which can be repeated any number of times, but under more or less similar condition, but the way outcome of the experiment may not be the same from repetition to repetition and person to person, and at least it has more than one two, at least it has two outcomes, that is it is more than one outcome. So we have the following characteristics for the random experiment. It is performed according to some set of orders or rules. It can be repeated arbitrarily often. The result of each performance or experiment results on different outcomes and they have a chance of change. So such an experiment is called the random experiment. These are the main characteristics of the random experiments. So example is a toss of a coin. Once you toss, it may be have that, it may get an head or tail. So once the first time you get an head does not guarantee that on the second time also you get the head. Here are some examples which are random. So flip a coin, you got the outcomes are head or tail. Roll a die, the numbers from 1 to 6, any number 1, 2, 3, 4, 5, 6 will appear. Exam marks, if it is between 0 to 100, so the maximum mark is 100 and minimum mark is 0. Again, correspondingly, you have a grade A, B, C, D, and F. So all these are some random experiments. So these are some more random experiments which can be we can observe in and around us, like lifetime of a computer, number of accidents in a day, number of persons arriving at a queue, like that. All these are uh, real life random experiments. Okay, now we define an event. Any outcome of a random experiment is called an event. An event is a set of sets or possible outcome of the experiment. Consider the case of a rolling a die. So the experiment can be defined as even number turn up or odd number turn up. Then we have two outcomes, so which is defined as E equal to 2, 4, 6 and E dash equal to 1, 3, 5. So now we can divide the E into again smaller outcomes, that 2 turn up, 4 turn up, 6 turn up, that is E1 equal to 2, E2 equal to 4 and E3 equal to 6, and also E can be written as E1 comma E2 comma E3. So in this case, since E can be divided into smaller amount, we called E as a compound event, and the E1, E2, E3 which cannot be further divided into another smaller type, they are called simple event. So we can have three definition here. One is called the event, other is the compound and simple event. So what is sample space? An event which can be divided into smaller events are called common event, and the event which cannot be further divided into smaller event is called the simple or event or sample point. A sample space is the set of all sample outcome or sample points of a random experiment. For example, if we roll a die, the sample space is S equal to and is 1, 2, 3, 4, 5, 6. So sample space is usually denoted by the letter capital S. So these are some notations that we are going to use further in this class. So we let A be a set, then notation X element A means that X belonging to A, or X is a number in the set A, or X is an element in the set A. So an event is a non-empty subset of a sample space X. We define an event as a subset of sample space, a non-empty subset of sample space. And again we say that E has occurred if any one of the event in E should happen. So if we have, for example, in this case we have E equal to 2, 4, 6. If we toss a die or a roll a die, then if we got any one of this number 2, 4, 6, then we say that the event E occurs. Okay. The sample space is called the certain event or sure event, because whenever you toss a die, any one of the numbers will turn up. 1 to 6 is turn up. So sample space is the set of 1, 2, 3, 4, 5, 6, and whenever you toss a die or roll a die, one of those numbers appears. So it is a sure event. The null event is an event having no point and is denoted by phi or null set. Null event is also called impossible event because it cannot happen at any time. So we can have one more definition: equally likely events. Two or more events are said to be equally likely if any one of them cannot be expected to occur in the form of the other. So because if you can have a unbiased coin, you have a equal chance of getting tail or head. So then we say that the event is equally likely. That means every possible outcome of the random experiment or every element in the sample space has equal chance of occurring, then we say that the event is equally likely. Otherwise, it is called unbiased events. So here are the some examples again, and their sample space, which we already discussed earlier. Tossing a coin, the sample space is H and T, and E equal to set H is an event. Again tossing a die, sample space is 1, 2, 3, 4, 5, 6. If E equal to turning up of even number 2, 4, 6 is an even. Tossing a coin twice, then the sample space become HH, HT, TH and TT. Any set E, HH and HT is an event. So tossing a dice twice, you get 36 elements, 1, 1, 1, 2, 1, 3 up to 1, 6, like 2, 1, 2, 2, 2, 3 up to 2, 6, 3, 1, 3, 2, etc. 3, 6, 4, 1, 4, 2, etc. 4, 6, 5, 1, 5, 2, etc. 5, 6. Then 6, 1, 6, 2, etc. 6, 6. Altogether, there are 36 paired observations. So these are the some examples. Especially example 8 is a continuous experiment. For the result is as a continuous, it's a plane or a part of a plane. So that's what it is, a continuous type of random experiments. Okay. We divide again the experiment or sample space into two. One is called the discrete and other is called continuous sample space. The sample space of a random experiment is said to be a discrete if either of the following occurs. That is, it contains a finite number of points or an infinite number of points which may be arranged in some order and counted. That is, we can put it to one correspondent with the natural number 1, 2, 3, 4, etc. So in the above we have discussed how many experiments in which 1 to 7 are discrete sample space, corresponding to discrete sample space. The sample space of a random experiment is said to be continuous if it contains a continuum of points. So if you take the height of a student in a college, so that may be vary from 4 to 6.5 feet. So normally it is 4 to 6.5 feet. So it can take any number in between 4 and 6.5, both included. So that is it containing an infinite number of points in between 4 and 6.5. So that is called, it is a continuum of points. Okay. Next what is we have operation of events. So the two events E1 and E2 are said to be equal if every element of E1 belonging to E2 and every element of E1 belonging to and every element of E2 belonging to E1. So and is defined as E1, E2. So if we take E1 equal to 2, 4, 5, 6 and E2 again is 2, 4, 6, then we say that E1 and E2 are equal. So whether example is here, if E equal to 1, 2, 3, 4, E2 equal to 1, 2, 3, 4, then we say E1 equal to E2. Complement of an event. For an event E, the complement of an event contains the elements of the sample space which are not in E. So if S equal to 1, 2, 3, 4, 5, 6, E equal to 1, 2, 3, 4, then E complement is 5 and 6 because only 5 and 6 does not containing E but in S. Sub-event and super event. If in this case, in the above example, if S is called a super event and E is called a sub event, that means in sub event we can have the elements which are the subset of the super event. So the null event already specified is a sub event of every event E, and the sample space S is a super event of every event. So the union of U2 event. So union is usually defined by En union E2 or E1 plus E2. Means it contains the elements both in E1 and E2. Remember that if E1 equal to 1, 2, 3, 4, E2 equal to 1, 2, 3, 4, 5, 6, then E1 and E2 union E2 means the number of all the elements both in E1 and E2 without repetition. Don't if you cannot write 1 1, 2 2, 3 3, 4 4, 5 6. So here E1 is 1 2 3 4, E2 is 1 2 3 4 5 6. So E1 union E2 is 1 2 3 4 5 6, not 1 1 2 2 3 3 4 4. So you use only once the elements in the union, not repeat the event. So the intersection means the elements which are both common to the E1 and U2. In the above example, we can have E1 equal to 1, 2, 3, 4, E2 equal to 1, 2, 3, 4, 5, 6. And for both the elements, both the events, the common elements are 1, 2, 3, 4. So the intersection E1 intersection E2 is 1, 2, 3, 4. Okay. So you can extend it to any number of sets. It is not necessary that you have to find out the union of two. You can find union of any number of sets. So it's a finite or infinite number of sets. So as the case of intersection. So another way of defining complement is that occurrence of one prevent the occurrence of other. So if E occurs, then E dash does not occur. I mean, for example, when you toss a coin, occurring of head prevents the occurring of tail. So any one of them occur, both together does not occur. So that case is called the complement. So here are some properties of the or the operations of events. So first one is the commutative property. So E union F equal to F union E. Similarly, intersection F equal to F intersection E. So you can intersects, but the result remains the same. So associative property. So E union F union G equal to E union F union G, or similarly is the case of intersection. So you can find the union or intersection in any order if with more than 3 variables, more than 3 events. Again, next one is the distributive property. That is A union F intersection G equal to intersection G union F intersection G. That is again E intersection F union G equal to E union G intersection F union G. Then we have a De Morgan's law, which is the generalization of the above result. So you can find a union n equal to 1, Ei complement is equal to intersection n equal to I equal to 1 to n E of complement. So complement of a union of any a set of events is the intersection of their complements. Similarly, the intersection of the complement of the intersection of any set of event is the union of the complement events. So it may be finite, you can extend it to infinite number. Okay. Like in some identities, which is always occurs or which is happens every time. So that is E union phi equal to E, intersection phi equal to phi, E union S equal to S, E intersection S equal to E. Again, E union E equal to E, intersection E equal to E. So E union E complement is S, E intersection E complement is phi, and E complement equal to E. Okay, this is only a mathematical or Venn diagram we call representation of what we are discussed so far about the properties of events. Okay, these are the general notation that we are used in coming course. So now we define a mutually exclusive event. The two events which cannot occur together are said to be mutually exclusive or disjoint. So I already mentioned that if we toss a coin, both the head and tail does not occur simultaneously, or the occurrence of one prevents the occurrence of other. So once we get an head, there is no chance of getting a tail in the experiment. Once you repeat it, it may be there, but for the first given experiment, it happens any one. Both of them does not occur together. So such events are called disjoint events. You can extend it to any number of times. So here they say if E1 is defined as the occurrence of head and E2 is defined as the occurrence of tail, then E1 intersection E2 equal to 5. Okay. So if otherwise, and another example which cannot be independent is that if you toss a simultaneously a coin and a die, then the occurrence of a head and occurrence of a even number on the die will happen. So they are not mutually exclusive or disjoint. So now we come to the sigma field of event. So any set of sets. So if we have a sample space 1, 2, 3, and we define a set B which is called the set of sets. Like here it is defined as, you can see in the last it is S equal to, we take 1, 2, 3, 4, 5, 6, the tossing of coin. E1 is defined as the odd number turn up, E2 is defined as even number turn up. Then B is a set of sets, so it contains E1, E2, 5 and S. So that is called the Borel measurable set or Borel field. And if this Borel field or Borel set is called a sigma field if it is closed for complementation and it is closed for intersection. That means if you take any sets of or set and their complement, that should be in B. So if I take E1 1, 3, 5 and its complement is 2, 4, 6, which is here in B, this one. So this is in B. Likewise, if I take S itself, then S is here, S complement is 5. So again, if you take any union of this set, if you take the union of this one and this one, the union become this one. So it is in B. The third one is if you take a intersection of any two sets, if you take the intersection of this set and this set, that is 5, which is here. So if you take, so like that, if you take the intersection of this one and this one, this is 1, 3, 5, it is also here. So if you take any combinations of union, intersection, that should be there. And if you take any set, its complement should be there. If you can construct such a set of sets, then it is called the sigma field or sigma field of events. Thank you.